This question is taken from the ENGAA 2020 Section 1 paper, and it is question 19. The question reads, a rocket travelling in space burns its fuel at a constant rate. By expelling the burnt fuel, the engine is applying a constant force to the rocket. What is happening to the magnitude of acceleration of the rocket? So we are given these choices of answers, and we have increasing at an increasing rate all the way down to decreasing at a decreasing rate, with the middle option of not changing for the magnitude of the acceleration. So this question seems quite hard on the surface, and it is, but how could we think about it? How could we get the magnitude of the acceleration? So normally people would think, let's use F equals ma, because we've got a constant force. But then the mass itself is changing. So this is one of the cases where we can't use that assumption in Newton's law of F equals ma. The proper definition of Newton's second law is force is the rate of change of momentum. So it's a change of momentum over change in time. This is the definition of Newton's second law. So the change in momentum can be due to kind of two things. So we could either have a mass times a change in velocity, or at that velocity the changing in mass, a change in mass. So change in momentum is m delta v plus delta mv. So these are the two routes for the momentum to change, because we are burning fuel, so the mass will change. So we'll have this part, delta mv. And then if we divide this by the time, then we have F equals m delta v by delta t equals delta m by delta t times v. So we can write this as F equals mass times acceleration, which is the rate of change of velocity, and then m dot, which I've given this letter. So m dot is the rate of change of the mass, because we're burning fuel, and then times the velocity here. So we know m dot, the rate of change of mass, is going to be negative because it's burning some fuel, or burning mass essentially, and it's a constant. So we could call m dot as minus k, for example. So constant rate of mass decreasing. So if we rearrange this to get the acceleration, then we have F plus kv equals ma, and then F plus kv divided by m equals the acceleration. So what will happen to this acceleration over time? Well, we know as it burns some mass, or it's expelling that burnt fuel in another direction, then due to conservation of momentum, then the velocity of the rocket itself must be increasing in the forward direction. So imagine we're expelling mass in one way, then the rocket's velocity must be increasing in order to compensate for this negative change in momentum for the other part. And then also we're burning mass, so the mass will keep decreasing as well. So the part on the bottom will keep decreasing. So due to conservation of momentum, the velocity is increasing and mass will be decreasing of the rocket itself. Well, the rocket in total with the fuel. So this is really the total mass of the rocket plus the fuel. So we know that the acceleration will be increasing, but is it at an increasing rate, constant rate, or decreasing rate? Well, one way we could picture this intuitively is that as the acceleration is increasing with increasing velocity, we could see that if we just had F plus kv, then the acceleration would be a straight line going through F, or minus F, and then a gradient of k in this case. So we could imagine it as a straight line. But then as the mass is decreasing, you could say the gradient k over m in this is one way to think about it, is the gradient will keep increasing because k is constant but m is going down. So the gradient of the line, so a against time, will keep increasing. So the acceleration is increasing, but at an increasing rate as well. So the answer is A. So you could think of the acceleration as increasing at an increasing rate. So the more mass you burn, the more you're accelerated, and this will keep accelerating at an increasing rate. Another way, which may be easier for someone else to picture, is that we have some 1/m dependence here. So as the mass keeps decreasing, then the acceleration should be shooting up really quickly. So whenever you're dividing by m, which is itself decreasing, then it will keep shooting up rather than flattening off. So if you took m to go towards 0, then this would approach infinity, which would never really happen, but it's a good way to picture what's happening in this scenario. So the answer is A, increasing at an increasing rate.